The graph refused to agree with the spacecraft. A thin line on a navigation plot began drifting away from every prediction engineers trusted. The difference was almost impossible to notice, yet it never disappeared. The measurements were precise enough that respected scientists began wondering whether the laws governing the solar system had failed before they fully understood the machines carrying the instruments. The force looked almost insignificant. If it slowed a car traveling at highway speed, the car would keep rolling for nearly 10 million years before finally stopping. Yet that tiny effect was enough to pull 2 deep space missions into one of the longest-running mysteries in modern space exploration. The plot became the evidence. John D. Anderson and the navigation team at the Jet Propulsion Laboratory compared Doppler tracking from Pioneer 10 and Pioneer 11 against trajectories calculated from general relativity, planetary gravity, and solar radiation pressure. The 2 spacecraft were heading into different regions of the solar system, but the residual plots developed nearly the same quiet separation. Both appeared slightly closer to the Sun than the calculations predicted, as though an unseen force was gently resisting their outward journey. A single unexpected measurement could be set aside. Thousands of them, collected over years, could not. The first response was not to question physics. It was to question everything else. Navigation software was checked. Tracking systems were examined. Planetary masses were reviewed. Engineers searched for leaking propellant, faulty telemetry, overlooked corrections, anything ordinary that could explain why both spacecraft behaved almost identically. Nothing erased the line on the graph. That persistence changed the investigation. Every conventional explanation that disappeared made more radical possibilities seem a little less unreasonable. Soon, the spacecraft were no longer the main suspects. Research papers began exploring ideas far beyond engineering-modified gravity, alternative interpretations of Einstein's equations, and other proposals for why gravity itself might behave differently across enormous distances. For more than a decade, the anomaly remained one of the strongest hints that accepted physics might be incomplete. The surprise was not that these ideas existed. It was that the measurements had become careful enough to deserve them. All through the debate, the graph kept returning. Correct one source of error and the separation remained. Remove another possibility and the same gentle drift survived. The picture did not become more dramatic. It became harder to dismiss. Eventually, the investigation turned somewhere few expected. Not toward larger telescopes, not toward new theories, toward cardboard boxes. Inside storage facilities at the Jet Propulsion Laboratory and the National Space Science Data Center, obsolete 9-track magnetic tapes still held decades of Pioneer telemetry. Many had been written in formats modern computers no longer understood. Some had physically deteriorated with age. Recovering them became a forensic operation, not a laboratory experiment. Slava Turyshev and his team began locating, cleaning, transferring, and decoding the recordings before more information disappeared forever. What emerged was not another set of navigation measurements. It was the spacecraft's engineering memory. The recovered streams revealed temperatures, electrical power, instrument status, and the changing behavior of systems that had been operating continuously since launch. For the first time, investigators had enough information to reconstruct the spacecraft in detail. Instead of treating them as points moving through space, the question quietly narrowed. Maybe space was not behaving strangely. Maybe Pioneer had been doing something no one had fully measured. Attention settled on the spacecraft's source of heat. 4 radioisotope thermoelectric generators, powered by plutonium-238, had produced roughly 2,500 watts of thermal energy at launch. Almost all of that energy became heat. Heat leaves a spacecraft by radiation, and radiation carries momentum. If more heat escaped in one direction than another, even by a tiny amount, the spacecraft would receive an equally tiny push in the opposite direction. That possibility had been discussed before. Now it could be tested against decades of real engineering data. The recovered telemetry allowed engineers to build a detailed three-dimensional thermal model. Every surface, every compartment, every changing temperature contributed to calculations showing how heat flowed through the vehicle and into space. Reflections from the backs of instrument compartments and the geometry around the power generators created a slight imbalance. No thruster fired. No component failed. For years, the spacecraft had been pushing against itself with escaping heat. The predicted recoil force began tracing the same path that had puzzled investigators for years. The graph returned once more. This time, another line appeared beside it. Measured acceleration. Modeled thermal recoil. Instead of drifting apart, the curves settled onto one another with striking agreement throughout the mission. The unexplained acceleration, about 8.74 times 10 to the minus 10 meters per second squared, directed toward the sun, could now be reproduced by ordinary engineering. The universe had not changed. The understanding of the spacecraft had. For years, the strongest evidence that physics itself might be broken had been generated by machines everyone believed they already understood. Solving the anomaly required forgotten telemetry, decades of engineering history, and a willingness to follow the measurement back inside the spacecraft. The final image remained the same trajectory residual plot that had started the investigation. Only now, the separating lines no longer pointed toward new physics. They matched the quiet, continuous recoil of heat, leaving Pioneer 10 and Pioneer 11 exactly where it had been all along.